Well, it's a great pleasure this afternoon on President's Day to welcome Professor Monroe Kennedy III, who is an assistant professor of mechanical engineering at Stanford. And we're very happy you're here on this holiday to present your work to us, Monroe. So Monroe is, he's joined Stanford recently after finishing his PhD at UPenn in the GRASP lab, working with Vijay Kumar and collaborating with Kostas Danilidis on some problems during his graduate work, which involved robotic manipulation of really interesting tasks like pouring liquids and precision pouring. So things that you'd, in a bio or chemical lab, you'd want to do with high precision. And that involves not only, just visual feedback, but also calculating by, the visual feedback volume and understanding and, figuring out when you have to stop pouring so that you get a very precise measurement. So some really nice work there. Since joining Stanford, Professor Kennedy has started the Assistive Robotics and Manipulation Lab, or the ARMLab at Stanford. And his focus there is particularly on the design of robotic systems that collaborate with, or that are meant to collaborate with people. He's won several awards during his PhD, and we're delighted to have you here. Thank you, Monroe.
Thank you for that fantastic introduction. I'm happy to be here and hope you enjoy the talk. So today I'm going to discuss considerations for human-robot collaboration. I started the Assistive Robotics and Manipulation Lab with the overall goal of looking how to develop intelligent assistive technology that improves human life. And classically, this falls under the realm of robotics. And so the three main areas that our lab addresses is robotic assistance, intelligent wearables, and connected devices, where each of them kind of cover different aspects of how you might want a robot to work with a person. And throughout the talk, especially toward the end, I'll really cover some examples of current projects we have that fall under each one of these categories. The overall question that our lab is asking is, what's really the barrier from having a robotic assistant in people's homes right now, right? To that, many things might come to mind, but I think, as some of the solutions kind of emerge, we're seeing that possibly the harder things are really being able to complete really complex tasks, or work in complex environments, and often work with a human collaborator. To do those things successfully, we find that the robot must have a really good understanding of how everything interplays together. How does the robot model correlate with the task? How do both of those correlate with the human model in order to be a successful teammate or assistant? So I started this lab in late 2019, so autumn 2019. And in that time, I've actually been very lucky to find many fantastic individuals, and you'll see their photos pop up on their work later in the slides. So let's kind of think of a timeline that kind of led us to this point. So in the 80s through the 2000s, automation was really the big thrust. How can we have these robots do very repetitive tasks well? Their environment is very well constructed, but we need them to work effectively and repeatably. We see the emergence of autonomy, where we want these systems to work well in unstructured environments. They need to know where they are, what they need to do, even when the world may be less structured. We see the emergence of centralized swarms. So these are groups of robots working together to possibly perform very complex tasks. And then as these go to scale, we actually need these systems to become decentralized and still work together, and possibly in sometimes around people. And then finally, and this actually goes, you can think of this both for the Amazon Kiva robots and even for this picture we see here, we have this stage now where, again, the system of collaborators are decentralized, but some of those collaborators may in fact be people. So in this kind of space, to kind of calibrate ourselves to the types of problems we might be interested in, what we can ask, does effective human-robot collaboration possibly look like? You could think of perhaps wanting to carry a table with a human counterpart. You could think of a wearable device that's able to observe the environment and provide useful information back to the person who's wearing it. You could think of a system where you can easily describe what you want the robot to do, and then have the robot work alongside you in a way that brings optimality to the entire team. You might have a wearable device that actually augments or replaces a component of the person, perhaps restoring an ability that they lost. You can imagine these sort of systems in the driving scenario, where the system is able to present risks to you and actually have some form of shared or parallel autonomy. And even, again, you can have ability enhancing devices, devices that take a skill like interpreting ASL and are able to actually meaningfully do that for you. And so in this space, this is just a few examples of what we could classify as augmenting, collaborative, assisting robots. So the questions I'd like to ask in this talk are: one, what makes an effective collaborator? What tools do we have, and what do we need to make robots effective collaborators? And what must be considered for human-robot teams? So let's start with what makes an effective collaborator. So many of you might actually recognize this video. If we go back to think about how we actually made robots, many groups of robots work together effectively in the past, usually they were centralized, like in this example, but they could also be decentralized. And the key was having some sort of digital communication that allowed them to work effectively together. When you do these sorts of tasks with groups of robots, if the system, especially if the system were decentralized, it's extremely important that all of the agents have consensus on the desired behavior, and every agent know or be told what their role is. So this is how we could do this when we have the ability to digitally communicate these high-level objectives to other agents. But if we look at biology, biology is able to do a fantastic job even without digital communication. And so when we look at these amazing feats, the question we should ask is, what makes such a team effective? I would argue that the points that allow this to occur are shared goals and objectives among teammates, the ability to model your teammates' behavior and use that for prediction, and the ability to plan given personal and teammates' roles. So often these sort of biological agents perhaps have to perform teamwork with very limited communication modalities. Some I'll touch on are audio, vision, and tactile, right? So if you think about audio communication, it allows for high specificity, but it can be very slow, right? And it may take time to describe a complex task to a collaborative agent. When you think about vision, observation can be done mutually. As you see in this video, the dogs are able to look at each other and they determine where they should be placed in order to guide this herd. So it can be very fast and very detailed. So here, this is statically, they observe each other and their strategy is conditioned on the actions of the other creatures here. But also you can think of scenarios where desired action is actually described by just observing your agent over time. Here, so an example we all know of is having a bee actually describe the path it wants the rest of the hive to take in order to find food. And finally, in the space of tactile touching, this can also be a very fast form of communication. But as you can imagine, proximity is a requirement. You have to be close enough to actually extract or send that information. And so here in this example, the soccer game is actually being described to the gentleman in the middle. So key features of teamwork are role understanding. So given the actions of others, what is my role, and is my role unique given the task? And also, I would argue interagent trust, which I'll define as A, having an agreed objective, and B, having a known behavioral model. And these two couple together. So in this driving case, right, the basis for red to trust blue is that A, there has to be an agreed objective. Blue doesn't want to collide. And second, the behavioral model will respect that objective. Blue will maintain a velocity to achieve the objective. And based on that trust, red can then take that lane changing action. So what are the limitations when we specifically think about these sort of biological systems? We have limited communication modality, we have limited dexterity and strength to weight ratio, and possibly limited perception. So what do these biological agents do to overcome them? They have task understanding and the role understanding, and they also do teammate modeling to overcome these. So let's think about what we have in robotics that might allow us to begin to approximate that. So some high-level concepts I'll cover are proprioception and control, perception, and intelligence. A lot of you are very familiar with these, but I'll present these as a high level to pull them into the other phases of how we might address some of these problems. So with that proprioception component, you have the ability, for instance, in a manipulator, and having a background in manipulation myself, I'll kind of stay and ground a lot of my examples here. But for kinematics, right, to predict where your system will be given measurements, internal measurements of your state. You may have knowledge of your dynamical model that tell you how you expect your state to change given the complete state and the dynamical parameters of your system. If you want to actually plan the motion, right, of your system through, let's say, obstacles, we have motion planners that allow us to accomplish that complex task. Often they're sample-based. And if we want to control force on our system, often we have some knowledge of inputs we can do that allow us to change the state in a desired way. If we focus a little bit more on instances of contact, right, and those that lend themselves to this, like with manipulators, you might have a balance between whether you want to think about impedance control or admittance control, and often that's based upon what your inherent task is. Where often the role in impedance control is to actually model, allow your system to model a desired mass of the system or an impedance to an external force that's being applied. And in admittance control, you perhaps want to respect the desired position that comes from an external force. Such that you can actually react and adapt to that external contribution. In the space of perception, right, we have camera sensing, which I would argue is one of the most powerful sensors there is, and it's a gift that keeps on giving. We have laser-based rangefinders that allow us to actually actively perceive our environment. We have tactile sensors, which allow us to touch our environment as well. So of all of these, I would argue the thing that probably you would argue keeps robots out of your house right now, messing with your dishes, just being free to do things in your house when you're away, I would say is really the tactile sensors, right? You might be confident that the robot can drive through your home, but how confident are you that it can actually safely handle your wine glass? I would argue very few of us even today have that sort of confidence, right? So this is where we want to be. This is work done that actually has these cameras looking in at the Rubik's Cube from outside. This was built in RL, and it's actually solving this Rubik's Cube in hand with these external cameras. The tactile sensors in the hand at this point are not being leveraged. But with all of that, this is an impressive feat, right? And if you could transfer this ability to any type of manipulation task, this would go a long way, I think, in having us trust that a robot could operate efficiently, let's say, in a home environment. So thinking about where we are, there's a whole space of sensors we can think of, but some of the leading approaches actually leverage vision. So here you see a gel site sensor grabbing a ball, and you see the normal, and when it pushes down into the peg, the shear forces of that contact. And that's extremely important when it comes to wanting to perform in-hand manipulation. So getting an idea of the space of these sort of tactile sensors, we have sensors that are good at just getting the normal force from the system, and a lot of those are mechanical, like using piezoelectric. On the onset of 2D vision-based sensors, your resolution shoots up, right? But a lot of the traditional sensors have a very flat surface and a single camera, which makes them able to sense in 2D. If you wanted to pick an object off the table, this would still be very challenging because the sensors are in fact 2D. We have this sort of 2.5D sensor here, the soft bubble pneumatic vision based, and it also is extremely capable. And then out of actually Berkeley, we have this amazing 3D shaped vision based sensor, which is really taking us large leaps ahead toward being able to do these types of manipulation. And so a question I began asking one of my students about a year and a half ago now was, what would it take to actually bring this all the way home, right? We need a really good design for our sensor that can leverage anthropomorphic inspiration in a curved fingertip and be able to deform and sense friction. And then once we had that, instead of jumping all the way to the end and thinking of an end-to-end solution, can we leverage some of the strengths of mechanical engineering that's been going on for the last 30 years in grasping and actually model those types of things like the wrench cone, right? Or the limit surface, right? And if we have that, could that actually make the motion planning that actually has learning built into it more efficient because we've narrowed the search space based on mechanical models that we have some knowledge about? So to that end, my student Wang Kyung began to develop this sensor. So the current version here is actually using a fisheye lens that's able to observe the boundary of an internal hemispherical fingertip, where we illuminate the interior with LEDs, use that image data to then extract depression and then forces from our sensor. And so the main idea with this, and a later version here actually removes the glare that you see in this current picture. But the idea is by using the illumination from different angles, when you have some depression, the shadows that are cast by the Lambertian surface are used to determine what the height is at a point of contact. And then we realized that instead of keeping these lights stationary, if we actually allowed them to rotate much faster than the contact is actually occurring, then you can actually get different perspectives of that contact. And our goal is to test and see how much that improves the operation of such a sensor. And so once we do this, right, our goal is to actually calibrate this system. So you have these picoflex sensors, which are detecting the deflection. And then we have one of the methods of getting force sensor for a single point contact, others that'll give us multiple points of contact. And we'll actually be able to calibrate this sensor for the forces that are applied on the boundary. So once we have that information, what makes this different than a lot of traditional sensors is, again, we're able to see this continuous surface, and we want to stay out of FEM modeling. And so this pushes us into thinking about how we might leverage neural nets and AI to correctly represent possibly curved surface. And if we can do that, we realize we can get some very interesting things, both about the normal forces represented as a vector field or speck over our deformed surface, even the tangent forces from friction, right? And if we have these, then we can actually have a continuous representation of the limit surface. And because we're using vision, even if we know what the limit surface is, we can determine where we are in that limit surface. And this will allow us to plan in-hand manipulation of different objects. So to kind of, phrase this in your mind, I actually used this picture from Alberto Rodriguez and MIT, where they actually used motion cones to actually describe the motions for planning in-hand manipulation. Ours will be a little bit different. We're thinking now about static wrench cones, which capture the full multi-finger grasp coming from modeling a curved and continuous surface. And we realized that if we also incorporate a stochastic model in this, this also could provide measures of uncertainty for where we're grasping, like the angles, the forces, the friction. And if we have that and incorporate that in our planner, then we can also begin to talk about safe grasps in addition to stable grasps as well. So I'll close the chapter here on tactile sensing being what I believe is a very important thing that must be investigated and is of interest to our lab. In the space of intelligence, right, we can consider many tools that allow robots to predict behavior in this sort of cooperation paradigm. I love this taxonomy that came out of Marco Pavone's lab here at Stanford, where he kind of breaks down the different types of modeling when you're trying to predict behavior into ontological methods and phenomenological methods as well. A lot of the time, I think it's safer to think about data-driven structures when you know less about what it is you're trying to characterize. And often, if you're trying to model specifically human behavior, unless there's some underlying physics involved, a lot of times there's some sort of stochasticity, which kind of pushes you again into this generative approach bucket. When you think about robotic consensus and swarm behavior, right, and how they're kind of progressing, right, you have all of these advances in this space that come from a centralized system like an oracle that determines actions of all agents. You have cases where you have a shared plan and all agents act independently toward a predetermined goal. And then in some cases, when there has to be decision making, often that becomes a consensus problem where there's some form of voting that occurs. And the question often becomes, what's the most efficient way to actually perform that sort of voting and consensus? Okay, so we've looked at all of these tools that we have to actually, leverage toward this objective. But what does it take, right? So the key challenge for human robot teams is, one, digital communication is unavailable, right? And so what do robots need to be effective teammates for humans? So I would argue they have to have the ability to model complex tasks. They need the ability to interpret and manipulate environments configured for humans. And they need the ability to model teammates' actions and roles. So to this end, what I'd like to do is actually discuss these two main spaces of what you might think of in terms of a robotic collaborator. And I'll actually highlight projects in my lab that are beginning to address some of these. And through this, you'll actually see some of the math that we're actually using to try and accomplish this. And some emerging patterns will be observed. So if we think about wearables, particularly those that might actually substitute an ability of the person, then the question we have to ask is, what part of the human is being augmented or substituted? So here is like a very easy sketch of different components of the body being modeled in a simple control paradigm. So if there's replacement, is the robot augmenting the augmentation functionally adequate? Is it able to do what you need it to do? And does it feel natural or easy to use? So this work is done by one of my students, Shivani Gupta-Sarma, and master students, Gabriella as well. And the idea here is, can we actually build a prosthetic that's intelligent? Two minds, one goal. Can we actually improve the ability to get back a lot of the dexterous manipulation if you lose a lot of your arm, perhaps all the way up to your shoulder? There's been previous work that looks at the amputees that have elbow dysarticulation, but not as much that have actually looked at the shoulder itself. There was some amazing works out of Johns Hopkins quite a few years ago that began to do this, and we want to further that by bringing in intelligence to the conversation. So to accomplish this, right, I want to draw that diagram I did before, right, with the robot, human, and the task, right? The really hard part is often actually understanding what the human's intent, the underlying intent is. So traditionally we have EMGs, which are sensors that are able to measure muscle firing that are surface topological. You just put them on the person and they're able to get the firing from the muscles that remain. But if you had a shoulder dysarticulation, those places that you could actually get information from are actually pretty sparse, and that can be really challenging. Another thing is you possibly want to understand how is the person interacting with the environment. So maybe they don't have the ability to take action on the environment, but they do have the ability to observe it. And so if you can actually put something between the person and the environment, like a mixed reality headset, you could A, determine what they're looking at with like gaze tracking, and B, you could actually highlight things in the person's environment that you think they want to interact with and observe their response, and therefore have a back and forth where you're actually able to augment the task or environment and really understand what their underlying intent is. So let's go back to that kind of control loop, right, for the human, right? We have cognition, right, which consists of the planner, the controller, your brain fires to your muscles, which are your actuators, and then ultimately your body has some dynamics. And then you have some sensory feedback, some touch and vision. I would argue, right, that to some degree, we actually have all of these components in robotics. They may not function at the same level or efficiency as the human body yet, one day, but I would say there are present. We have cognition, we have the plant, we have sensory feedback. So if I begin to think about the able-bodied person, right, the planner, controller, actuator, body dynamics, some sort of feedback through vision and touch, and all of this is interacting with some environment or task. Prosthetics as they are today, right, particularly ones that get information from EMG, simply replace that actuator and body dynamics component. Some that might have some really base level basic reflex might also incorporate, let's say, some vision and touch. What if your prosthetic touches something hot? It's easy enough to just move away from something hot, these sort of basic reflexes. But what we want to do, right, is actually have a robot that has this parallel ability. It takes some information from the person through mixed reality and the EMG, incorporates that with its own understanding of the environment, and is able to be a really effective collaborator. Again, I think the augmented reality component can't be stressed enough, from the ability to actually perform gaze tracking to having contextual understandings of the environment, leveraging the advances we have in computer vision. So I want to give you this kind of scenario, right, to imagine what this might look like if we could bring this to life, right? So an ADL stands for an activity of daily living. And imagine that ADL here is simply eating some food with a cup of water here, and you want to have this pitcher to refill your water. You could imagine using a very simple state machine that would model how you'd actually behave in this type of scenario. And so if you wanted to reach with your right hand and your right hand's a prosthetic, you might want to either grasp the pitcher or the fork. The little plus sign in the middle might be an indicator of what you're focusing on visually, gaze tracking. And then, once you have the pitcher, right, maybe the gaze isn't as important as possibly an EMG, because there's a lot of context in this task. Once you are holding the pitcher, you're most likely going to fill a cup. If you know where the cup is, maybe you only need a low dimensional input to actually drive that action at that point. And then when there's a split, maybe vision might become more important at this point, along with EMG, to make sure you're doing this at an operation tempo that's comfortable for the user. And then possibly once you have a repetitive task, like an EMG trigger to kind of feed yourself, again, having a lot of task knowledge, where should the fork go? Maybe you don't want a lot of fine-tuned control for that. If the arm has the ability to observe the plate, it might have a really good idea of how to feed the person based on its observation of the situational state. So let's sort of formalize this, right? I might have the state, which could include the arm and environment. I have the gaze from the person, some vector, which might be like a conic section. I have the EMG input from the person, and then I have some robot action, which may be discrete or continuous. And so the probability that the human wants to perform some action can be represented here as a probability of AI. And perhaps you have a finite set of actions such that this sums, for instance, to 1. And so what we want to do is predict what the human wants to do, what their intended action is, given the state of the system and their inputs, the EMG and gaze. And we realize that to accomplish this, if we can actually first understand the human's behavior, right, what would they fire their EMG, and what would they look at given the state of a system and an action that they wanted to take? And what's the sort of situational context, right? Given a particular state of the system, what actions are even available, right? And in what probabilities? And so we can actually let this flow simply from like a Bayesian network sort of setup, which leads us to this principle that based on those 3 components, we can determine what the action we want is given the EMG, gaze, and state, where what's highlighted in green come from a behavioral model, and blue can actually be modeled as an intent, which is this sort of intelligence about the situation that you're participating in. And then once you have these probabilities, the argmax would be the predicted intent. So let's ground this in what this might look like in terms of an experiment. So here you have a person with a dysarticulation on their right side. The object recognition looks at a table and determines that there are 2 things you might want to interact with, the pitcher and the cup. So there's a task understanding here. If the cup is probably empty, there's a higher probability that you're probably going to want to reach for the pitcher in order to fill the cup. You have gaze tracking that's kind of looking in this general area, but as it is, maybe that doesn't give you a ton of information, but it tells you you're on the right track, that the things you care about are in fact on the table. And then as the person kind of fires, if you can kind of see the EMG, if they fire an EMG, this may be an indicator that they want to move in a particular direction. And that itself can also influence what part of the table or what things that person might care about. If you superimpose these probabilities over your task, right, this would actually help you understand what the predicted intent is for the person. So the question that follows from that is, how would you actually extract those probabilities for those different metrics that we talked about, the ENG and gaze based on the state and task, and even the situational action given the state, right? So to accomplish that, again, we find ourselves back in this generative modeling approach. I chose to, kind of represent this in the CVA architecture here. But here you can actually, condition those probabilities on a latent state. Right. And this is really great because, again, you may not want to operate in the high dimensional space of images. There's probably some inherent meaning here that you want to exploit. Right. And that kind of goes to the affordances of the objects you want to manipulate. And those affordances can actually be encoded in the latent space of your system. And so here you see this probability distributed over our latent space, which you could then solve with the elbow, and then go on your way with actually solving for what those probabilities would be after you have the appropriate data, getting these models from the appropriate data. So the things we want to actually learn are, what are the probability that you want to take a particular action given the state? And then what's that human behavioral model? What's the E and G that are expected given a state and action that you're telling the person you want them to complete? So because we can kind of break these up, this is fantastic. This means that we can train and test everyday settings, even with non-amputee subjects. So if you have many people that are willing to dedicate their time to teaching the logic of a scenario, right, you can learn that sort of model. And then that could imagine that being loaded up into an app store of, now you can do X, Y, Z, because someone trained you how to perform that, train the system how to perform that task. And then on the other hand, you have this, given a state and action, what are the E and G inputs? This you'd actually want to tailor to every single person that's there based on the surgery that they had, their own conditions. How could you actually, get the correct input given a desired state and action? And so this is a common calibration phase. So as you can imagine, this is a lot. And so what we're trying to do to begin to address this is my ingenious students, Shivani and Gabby, are implementing this in simulation. So we have a simulated arm, Luke arm, in Gazebo, and we have the HoloLens 2, and we have a checkers board that you see in Gazebo there. And the checkers game gives us a really easy way to get the probability of A given S, right? You know that you want to win. You have the ranking of different choices. With the so if you project this virtual game in your virtual arm onto a table, you can actually do the gaze tracking immediately as an output from the HoloLens 2. And we have EMG sensors that we're actually able to put on the person to actually get the EMG input as well. And so here on the right, you see actually a whole bunch of strategies that can come from actually thinking about the possible moves, playing them forward, getting a probability on which move will actually most likely lead to success, having a probability distribution over that. That would be the P, A of S, which you would then condition with the other components that are coming in. So after we basically do this sort of proof of concept in this virtual environment and work with people to see what works and how we can actually make this work better, our ultimate goal is then to begin moving toward actual activities of daily living. And once we do, the idea is, if you think about the task performance versus time it takes to become an expert, the goal is, if we have this intelligent arm, our hypothesis is that you'll go from this sort of gray curve here on the bottom, which is the original time it takes to learn something, and you'll see an increase in performance, such as the ability to dexterously manipulate something in the hand, and a decreased learning time, the time it takes to reach that capacity performance. And that's our objective and hypothesis for this sort of system. So let's go back to this sort of model for our wearables. What about ability enhancing devices? So maybe you're not replacing something, but maybe you're improving some sort of sensory feedback concerning the world. So this is one of our projects, the Smart Belt. The idea right now is to use it for fall prediction and prevention. But ultimately, we think once we get to a good phase, we can actually combine this with lower limb exoskeletons to help them as well. So in the exoskeleton phase, imagine you wanted to move very quickly, dynamically, perhaps jumping from rock to rock. And one-day parkour, right? I'm full Iron Man with this. So if you want to do these very impressive things, current methods actually intercept signals from the brain to determine how the lower limb exoskeleton should move. But the human is actually planning many steps ahead. In fact, you might only get a firing from the brain when you're right at the point where you need it to fire, to move. And depending on the inertia of your system, that just might not be fast enough given the time it takes for the signal to travel from your brain to wherever you're intercepting that signal to tell the exoskeleton where to move. But if you could plan ahead, just like the person is planning ahead, then you can actually feed that input possibly into your control law for your exoskeleton with some probability, and that might actually help you to do more dynamic things with a human and reduce risk of harm to the person. A more immediate objective is to actually have a wearable belt we can put on a person and actually predict their risk of falling. And so this is a really common problem with the elderly, and it is a huge cause for hospitalizations that occur. So our approach is if you wear this belt and you're able to look at your environment, can we actually predict the probability that the person might fall on some look ahead time, given what they've done in the past? And if that probability is high enough, alert the user that they may be at risk in the next few seconds. And we believe that in doing so, we might actually reduce those falls, which has been seen to be an effective way, vibrotactile response, to help reduce falls in individuals. And so our end goal would be to have a waist-mounted belt that's capable of getting the person's visual inertial odometry, seeing the surroundings, characterizing the obstacles in the walkable area efficiently, and then being able to predict, given the person's past path, predict their future path or the probability of paths over that path, predict their gait and their stability variance, where we call stability their ability to a measure of their Z vector. How much are they aligned? How much are they upright? And everyone as they walk has some particular sway, but that doesn't necessarily mean you're at risk at falling. Maybe if you go past 45 degrees, you will, but usually just your orientation vector itself statically doesn't tell you you're going to fall. But the variance in that actually can be correlated to instability. So for a person who's walking with a particular gait, if that begins to change in frequency, that might actually give you some indication of falling, particularly if the gait does not correlate to that change in variance of the person's stability. And so if we can predict that, particularly that variance, we can use that as a classifier on whether we think the person might be at risk of falling. And so this is the potential architecture that we have in mind as we're building this system. This is an early version, but we're doing parallel design. So don't worry, people who would want to use this, they look at this and they go, oh my God, please don't expect me to wear this hazard suit everywhere for this device. That's just not usable. We get it. This is research platform. We're actually looking now to see if we can actually implement this even on certain mobile devices, and we're very hopeful for that. So another in the sort of ability enhancing device, you can even think of this even more broadly, more loosely, even in interpretation, right? So if we look at a lot of sign language interpretation apps, a lot of them go directly from vision to their end goal. But in recent times, we've seen really cool advances in extracting pertinent features from the person's face and the person's hand and torso. And if you can actually use those, we believe we can actually bring these solutions, which are currently stuck in the heavy GPU requirement space, down to possibly a mobile or cloud computing space, which will allow for bringing together these communities in a very meaningful way. And so this is an older version. We actually have a much cleaner torso tracking now, but we feed this into a transformer, which then allows us to extract the person's ASL meaning. And so right now we're doing this on a German data set and benchmarking against that. But ultimately our goal will be to work with the ASL community to bring this translation app together to bring these communities together. So we talked a lot about wearables, substituting and enhancing devices. What about possibly external collaborators? So this is a really fun project that I am fortunate to be able to work with Professor Dorsa Sadiq here on human-robot teaming for cooperative transport. The idea is, we want to observe how humans are able to transport with implicit communication and transfer that ability to a robotic assistant to make the robot an effective transporting teammate. And so the question is, right, you have to have this sort of inter-agent trust in order to characterize the valid approximations of each other's objectives and strategy. So if we're carrying something together, if we know where we've been, if we have the observations of the environment, and there's a latent strategy, right, in how we're trying to behave, if we can predict that, then you can predict where your partner wants to go. So to achieve that, we were initially starting off with a physical system, and then COVID struck, so we got creative, and we figured we could begin with a digital system and eventually move back to the in-person carrying once that becomes safe. But in that process, we realized that the virtual environment gives us a really cool intermediate tool along the way. So if you think about the human-human demonstrations and then the robot-human learning and collaborator, you have, again, this ability, you want to watch people work together. Can you predict what their actions will be given the states and the surrounding environment? And then in possibly an RL teaming phase, you can use that imitation learned or learning from demonstration model policy pi sub h to help train pi sub r to be a good collaborator and possibly even a better collaborator with that virtual agent that can be run offline or in training in a traditional RL environment. And then in the real environment, we want to repeat the same thing. Watch people carry these together. The thing that they would carry would give us information about the forces that they're applying. We will be able to measure the states. We would also have them wear the augmented reality lenses so that we can actually put obstacles in their path and we know exactly where they are. And then have a human collaborator work with the robot and again, extract this latent strategy so that hopefully the robot can be as an effective teammate or even better than a human collaborator. Another project we're working on in this space is how to actually improve the efficiency of learning from demonstration and collaboration. So two sort of components to this. One is task description. If we have some knowledge about the physical nature of the environment, can that be conveyed to the robot to therefore reduce the amount of time it takes to train? If I'm trying to teach you how to open a door, we've seen the Google robots spend hours and many robots to do that. But if I'm having a demonstrator come in, maybe the demonstrator could highlight the rigid bodies and the constraints. The handle is a rigid body, the door is a rigid body, the hinges are constraints. These are the things you need to care about. Find that mapping in your perception, but this is a very simple thing. There are 4 things here that actually matter. Can you actually leverage those to help pass on that underlying goal and therefore hopefully help reduce some of these tasks down when you're trying to transfer it to the robot? And secondly, if you want to have the robot work alongside the person, perhaps sometimes the human may take suboptimal actions. If I have 2 boxes, a heavy box and a light box, and if the person carries the heavier box, it's going to make the entire team slower. If I observe the human continuously carrying heavy boxes and I, as the robot, I'm better suited to that, then based on that behavior, I should then go and begin moving heavier boxes, which would force the human to carry the lighter boxes and increase the efficiency of the overall team. And so accounting for, again, this sort of latent strategy of the person, how can we make the robot a more effective teammate? And even in cases where they want to plan out these scenarios to make the overall team more effective. The last project I'll bring up is one where we're trying to leverage human intent for shared autonomy. So in this case, we're asking, there might be some cases where you actually want to transition control at a non-zero speed between the vehicle and the driver. And this should be safe and smooth. So how can we accomplish that? So going back to this diagram, we have this this intelligent vehicle, we have, you know, the space in which you're driving, and then you have the human element, your driver. So if people want to drive, when does the robot take over control, and how can control be safely returned? So I use this this movie facetiously, but yeah, it might be a case where you want to take control over at some point. So let's think about how we actually do that safely at non-zero speeds. So a lot of you might be very familiar with this. This is the levels of autonomy, the 6 or 5 if you go from 0, levels of autonomy of automation for our systems. I would say these two, levels 3 and 4, are ripe for this discussion, right? You could have that full autonomy driving from the car, and the human could drive as well. So how can we efficiently pass back and forth in that scenario? So what are the risks from arbitrarily taking control from the human, right? Does the vehicle have an accurate model of the plant dynamics? And then what are the risks of giving control back to the human? Does the human have an accurate internal model of the plant dynamics and an effective control strategy? And this is particularly hard to answer. So how can we actually begin to address this? So I'd like to really give this scenario for arbitration. So imagine here you're driving along the road, and you want to give control back to the human, and there's some TS, time of switch, where you could have control authority just cold turkey switch from the vehicle to the driver, right? Then the trajectories from the takeover could remain in a safe set, which here would be your lane, or they could diverge from that safe set. Instead of handing over abruptly, you could imagine actually looking at the history of inputs and tell the person, hey, you're in control now. Observe their control inputs and determine if they would actually remain inside of a safe set. And if they do, right, then you could actually have some scaling that would then transition control from the vehicle to the driver. And we have some renditions on how we actually want to accomplish that transition. One would be to simply linearly scale from the control inputs of the vehicle to the driver. The other would be, if you actually have a behavior or latent strategy for the driver, have the robot switch from whatever its optimal RL version of driving is to the behavioral model, such that you can actually make this linear phasing approximation and transition control safely from the vehicle to the driver and remain in said safe set. And so you can imagine the control diagram for this consisting of a human action model, possibly a state transition model, as well as a robot action policy as well, in order to accomplish this, where the robot action policy, particularly going from robot to human, could be modeled in such a fashion. So the final takeaways are this. To be effective collaborators with humans, robots must be able to model human behavior and their role. There's a significant room for improvement in robotic hardware for alternate forms of communication, which include audio, visual, and tactile. And finally, robotic collaborators have the potential to expand their humates' capabilities, enhancing and restoring their quality of life. Thank you.
Thank you so much, Monroe. What a wonderful talk, and just sort of a focus on what's important, and then a broad range of projects that your lab is undertaking. So I think if you're willing to stay for a few minutes beyond 5, people will have a number of questions and a little discussion about this.